a little bit of this. In the ideal eye sight, the image of any object that you are looking at right now, for example, at the screen, at the book, around your house, will normally be projected on the retina. So light passes through the cornea, right? And is focused by the lens. So you basically have a lens behind the cornea on the retina, right? And then the muscles inside your eye, they change. And they change the shape of the lens. That's kind of the idea behind adaptive optics that we apply in astronomy. We change the shape of a mirror and a lens to focus an image of a star better, right? To make up for aberration or the atmosphere. Now, remember that everything, or all the information is governed by electrical impulses that come from the brain, right? And they travel through the nerves that they connect your eye to your brain, right? So if you guys are into biology or life sciences, you will be discussing this a little bit, where maybe not the physics in depth, but kind of the how this works, right? But then at the end of the day, right, you're gonna have an inverted image being produced here, right there. So the reason why you don't see objects inverted is because by evolution, the brain has learned to adjust images to appear correctly or properly, right? We know that even happens with animals. However, this also, or the fact that the eye has evolved differently for different animals, we know that, for example, some animals like birds can observe ultraviolet light. Or for example, dogs, as far as I remember or I know, they only see black and white, because the evolution of certain animals depend on the environment, right? So, or their needs, right? So in our case, our evolution has made up that the eye has evolved in that way, right? We look at colors only in the visible spectrum, and images that are supposed to be inverted, as you see there right now, are actually straight due to the brain adjusting it for us. So there are two cases, right? Remember that we've been talking about lenses, and depending on the position of the object, you can have different sizes of images and different positions per se. So depending on how your muscles react, depending how old you are, so you can observe distant objects and near objects by the ciliary muscles either relaxing or being tense, right? So that's how ideally your eye should work. And then you see the projection of the image on the retina. Clearly, if you have an object close to you, you can see it more clearly, right? Larger in there. However, what happens when you get older, or by any, for example, you can inherit any eye problems that you may have had in your family? So then you may have nearsighted, farsighted problems. You call them myopia, I believe, right? Astigmatism as well. So there are different eye problems that we have nowadays. In some cases, it's related to spending too much time staring at light, at the screen, at a computer, right? Especially back in the day when we had those old television screens, as I explained, that they use the cathode ray tubes, right? So in any case, regardless of the reason, we have different situations where you may have a near point and a far point. The near point is defined as the closest point where the eye lens is able to focus. Normally it's around 25 centimeters, but with age, right, it becomes less flexible. And then the far point is the farthest point at which your eye can focus, right? Now, just by doing a parenthesis, if we have a camera, right, just to relate it with the eye, it also uses a focal length and a convex lens, as you see there, to produce a film, especially all cameras. Nowadays they use pixels, right? So the idea for the camera or for the eye is to introduce the F number, right? And then the power of a lens. Depending on the eye or the camera, you have a focal length of your lens, and you have a diameter of your eye or the camera. The F number characterizes the size of the aperture by dividing the focal length by the diameter of the aperture. So if you think about it, right, a lens can be approximate to a circle, a circumference. So if you know the ratio between the focal length and the diameter of the lens, you have the focal number or the F number of a lens. And the power of a lens, it's not here, is just the inverse of the focal length in meters. So for example, if I tell you that the focal length is 30 centimeters, right? The power of the lens is not 1 over 30, will be 1 over 0.3. So 3.333 meters, 3.333 diopters or diopters, all right? So when you buy a lens, normally you buy them by the power rating, right? Like when you buy an appliance, because the power is proportional to the, or related to the focal length, right? But remember, to find the power of a lens, 1 over F, F has to be in meters, all right? And well, to understand corrective optics or near and far-sighted corrections, we need to understand combination. That's what we've been doing, combination of lenses. And if you think about it, that's similar to the problem I did today, right? Where you have a convex lens and a diverging lens. You have the image due to this lens, this object, and then you have the final image of this, sorry, what am I talking about? You have the image of this lens, sorry, and then you have the final image due to this image there, right? So this was the image of this object due to this lens, and this is the image of this object due to this lens, all right? The image from a second lens. All right. So, well, this is what we did already. Now let's understand the corrective object for nearsighted people. For a nearsighted people, we first have to define a far point. A far point is the limit to where you have a clear vision and a fuzzy vision. For a nearsighted people or person, that person can observe very clearly things that are closer to the eye. So within the far point. Beyond the far point, it becomes fuzzy. And that's because, as you can see there, the object is focusing way too close and outside of the retina, right in front of the retina. So the eye lens is not working properly anymore, right? For objects that are too far. So let me ask you a question. How will you correct this case? Think about everything we've been discussing. And for that, I will use the whiteboard, by the way, for this part. So how will you correct a person that has that problem? Right? You need to create an image so it's projected on the retina. Right? So the object is too far. So let's leave the slide there. And then let's go into stop sharing there. So the person, right, has a far point there. Let's call it far point, because if I put an F, it will be mistaken with a focal point. So this is the boundary between fuzzy and clear. So the object is here, right? Unfortunately, you always want to have objects that are in different positions. So your eye, right, that comes like this, by the way, and then we can exaggerate like this. So this is your cornea here, right? And then that. What's happening right now is that without a lens, you are projecting the image around here, right? So there. But your retina is here. It should be here. I need to create an image that is at least here on the far point. So how about this? What lens is this? This is my concave lens. If you remember, I can light goes like this, and then it diverges. So let's make it diverge in such a way that the image is here, right? And then like this. Like that. So that image now of this object is there. And now, if I use this, this will be exactly on the retina there. So to correct for near sight, for near sight, we use a concave lens. You know what makes this tricky is that, I don't know, whoever uses lenses right now in class, you can probably tell, but depending on the eyesight, you may have, you probably, when you go to the ophthalmologist, right, they take your measurements for both of your eyes, because one eye might be able to observe objects properly, but the other one not. Or one eye might have need for a higher focal length, right? Because how do you decide what focal length to use for that particular lens? You have to take your measurements, right? But one eye might be stronger than the other. So that's what makes it tricky. So then you start having bifocal lengths, right? So this is a simplification of a medical issue of your eye, right? But it can get more complicated. So if you go back to your slides, right? There it is, right? So the image formed by a concave lens gives you an image on the far point. And basically that's how you correct for the eyesight, all right, for a distant object, okay? When we do the problems on this, the object is always positive. When we talk about virtual objects, but every object that you are looking right now is positive, right? You are looking at anything that is real. The image that is formed by the concave lens on the far point is virtual. So when you do the problems, you have to remember that if you're given the far point, and we're gonna do now the near point, that image that you are projecting to that point is virtual. So you need to have a negative sign there. And by the way, that's a refractive power. So when you get a lens, once they take your measurements, you get the lens based on the refractive power or the power of the lens. And again, the unit is diopter or 1/meters. All right, that's the strength of the corrective lens. Now we have the case of a far-sighted person, a person that can actually now observe things that are far, but it becomes fuzzy when they are close. That's probably not very common, right? You may think that it's more common the other way around. And it's true, but there are cases where a person cannot observe when things are too close. I don't remember the technical name, but the main idea is that now you have a near point. I can just put an N there. The vision becomes clear when it's farther from the near point, and it becomes fuzzy when it's closer within the near point. So similarly to what we did with the other lens, right? We're gonna have your eye like that, and then this becomes like that. And then, let's see, right? So when you are far-sighted, objects that are here you can observe. But if I place an object here, too close to the eye, it becomes fuzzy because you are projecting all the way there. So you have a problem there, right? It's behind the retina. You want it to be here. We need to create an image of that object that is projected here. So behind the object. The only lens that will be able to do that will be, as you probably already know, the convex lens. If I place a convex lens here, so that's what we did all, right? You will have and that will be projected all the way there. So this is your image. Again, is behind. So this will be virtual as well. So to correct for far-sighted people, you use a convex lens. Any questions about that? If you were wondering why we were doing all this, well, now you know, right? In biology, life sciences, microscopes, telescopes, there's a lot of applications for lenses. All right. Let's take a look what's left here. There. Right. Of course, I'm saying that it's projected here on a near point. It can be projected also behind a near point. Any point behind a near point is where your image becomes clear. Right? One question. How, I mean, right now we're using convex lens and a concave lens outside, right, of the eye, like a few centimeters away from the eye. How do contact lenses work? So how will this work if you were wearing a contact lens? What will change? What do you think will change if you were wearing a contact lens? The only thing, if you think about it, will be the position of the object and the position of the image, right? So when we start talking about contact lenses, it will just be this distance that you see here between the lens and the eye will just be 0. So then your object distance will be whatever this distance was plus the distance between the lens and the eye. All right? They will have to give you that information. All right? Now, since we've been talking about objects that are placed in between the eye and the lens, we also have to talk about the magnification. Now, we have been talking about magnification in terms of minus Q over P. That's called the lateral magnification. There is also something called the angular magnification. The angular magnification makes sense because when you look at, for example, a tree, and if you were to look at a tree through a lens, if the tree is very far, for example, right, or a building, there is an angle, right? Like, for example, hopefully you remember this from trig, the angle of elevation, right? It changes. So there is something called the angular size of an object, right? Which is the angle subtended from the retina. It's being shown to you there. It depends on how far you are from the object and the height of the object. And the angular magnification or the magnification due to the glass will depend on the height of the image and the distance of the image. All right? So for example, right, that's the real size and that's the image size. So you have a theta prime and a theta there, right? The angular magnification will be the ratio between these two angles, all right, here. So there. How will you use this? So if I use the trigonometry, right, and we have to remember a few things in here. So we're still talking about the eye, but now we're talking about the angle between the eye, the retina, and whatever you're looking at, right? Normally you look at objects that are very far. When we talk about the angular magnification, this is your eye, and you're looking at objects that are quite big and quite far. So your eye is making an angle theta. This is also very large, by the way. D naught. So I want you to remember the following. H naught over D naught is the tangent of theta. That can be approximately be theta. Why? Because it's small. It's a small angle. For small angles, tangent is approximately equals to sine is approximately equals to the angle. All right. Now let's talk about the image. So if you were to have an image due to this object, and you will also be looking at it, you have another angle here, theta prime. This is H. Let's call this H1, and let's call this D1. So again, this is the image. The magnification for this will be, or the size, sorry, will be tangent of theta prime, which is theta prime, equals to H1 over D1. So you have theta 1, or you have theta, and you have theta prime. So the angular magnification, let's call it like this, the angular magnification will be theta prime over theta, which will be the equation that you have on the slides. Similar, H naught over D naught over H1 over D1. But one question, how do you relate H1 over H naught? Minus Q over P. Tomorrow, we'll do a problem on that. All right, and near and far-sighted people. I want to leave it in there, guys, now because I need to run back home because of the storm and to prepare for the labs. But we're basically done with lenses today. This is the last application. Tomorrow, we're going to be doing a few problems on near and far-sighted people, which is basically lenses problems. And then I might, even though it's not going to be on the assignments, I might introduce a little bit of wave optics. So to talk a little bit about interference and diffraction. All right. What I also want to do tomorrow is, so tomorrow is going to be good weather anyway, so I can be here as well. I might do a couple of problems on review. But so far, you have everything now that is going to be on the exam on Thursday. All right. I'm going to be doing the exam today in the afternoon. So tomorrow I will have a good idea what's going to be on the exam. And I could probably throw you guys a couple of problems to review them. All right. What I would recommend you guys to do is just to finish homeworks 10, 11, and 12. That should get you ready, or even 13 as well, for the exam. All right. Are there any other questions? However, I want to go over on assignment 14, and I'm also going to go over assignment 15. Assignment 15, I don't think I will open it, but it won't be graded in the sense that you will have there for practice, because it has all the problems on near and far-sighted lenses that we did that I talked yesterday, the near point, the far point, and the power of the lens. However, I don't think it will be something that you will need for tomorrow anyway. All right. Now, let's introduce then the application of geometric optics to correct for sightness, for eyesight. The problem, or a problem that you can get, will be something like this. So let's have it here. They give you the near point of a person, right? So you want to prescribe lenses. So you have that the person has a near point of 50 centimeters. So a person has a near point of 50.0 centimeters. So 50 centimeters. And they ask you what's the focal length of the lens that you need to correct for that person, so that person can observe objects 25 centimeters away. So what should be the focal length to correct the eyesight, to correct the eyesight? And enable to watch and enable to observe an object 25 centimeters away. So when they give you the near point, you know that the person is farsighted. All right? If the person is farsighted, you remember that if you have a near point, you can observe anything that is here. But everything that is closer is fuzzy. So you need, if you have an object here within the near point, you won't be able to see it, it will be blurry. You need to make the image on the near point or farther to be able to project it on the retina. That's from theory. So the near point will be your Q. This will be your image distance. And your object distance is obviously 25. So the equation that we need to use is 1 over P plus 1 over Q equals 1 over F. But there is something else that you need to remember though. That the lens to correct is a convex lens. Right? For this type of vision. And has a focal length that is positive. So the answer should be positive. Now, what type of image is any image that you use to project when you are correcting for lenses? With correcting for your eye, sorry, with a lens, is virtual. So, right? The equation will be as follows. 1 over 25 minus 1 over 50 equals to 1 over 8. That's pretty much what you have to do. All right? And if you solve here, you get a positive F of 50 centimeters. So the corrective lens should have that focal length. That will correct for this issue here, right? And then they ask you, what will be the power of the lens? So let's do it here. To find the power of a lens, right? The equation for the power of a lens is equal to 1 over the focal length, but the focal length has to be in meters. The focal length is 50 centimeters, which is 0.5 meters, right? So 1 over 0.5 will be 2.0 diopters. Right? So you have already found the focal length and the power of the lens. But there are a few things that there is one little detail that we haven't taken into consideration though. All this is good if we assume that the lens and the eye are basically next to each other. But you know, if you wear lenses, right, like this, of course, there's always a gap between the lens and your eye. It can be a couple of centimeters or it can be a little bit less than that. right? It depends on the type of lens. So in the last part, they tell you that if the typical eyeglass is 2 centimeters in front of the eye, let's repeat the calculation of the focal length, right? Will that change? And it does indeed change, all right? So we're gonna now do this.
What is the units of power? What was the D?
Diopters, this. Diopters, all right? And normally when you buy glasses, they sell it by the power. As far as I know, they normally use, maybe not this exactly word, but they do it based on that, right? Only in science, like physics, right? If we're going to buy equipment for labs, we buy lenses according to the focal length, right? But normally, and the reason why you find them like this is because there is some thickness on the lenses. The equation, this one here, is normally used for thin lenses. So lenses that don't have a lot of thickness. As soon as you start having very thick lenses, right? That's when the equation might have to change and you have to introduce the indices of refraction. There is something called the lenses maker equation. You can take a look at it. I believe it was something like N1 over P plus N1 over Q equals to something. But there's a variation of that equation when you take into consideration the thickness of the lens. Anyway, so now we're going to use the same information, but now the lens is placed, or the lens is 2 centimeters in front of the eye. So what will be the focal length, right? If you think about it from the graph I had here, or I guess I can do it again, this was the near point. This is where you want the image to be able to observe it. And this is where the object was. And this is where your eye was. Right? Now we're saying that the lens is going to be, this is 2. So the object distance is not 25 anymore. This was 25. It's 25 minus 2. You want this. But also, the image distance is not 50 anymore. It's 50 minus 2 is 48. So the object distance and the image distance, they both get reduced by 2. And you may think that there won't be any changes, but remember the equation has inverses. So 1 over 23 minus 1 over 48 equals to that, right? So let's see, 48 times 23 over 25, right? Let's see what we get. And we can compare it with the previous one. So 48 times 23 divided by 25, 44.16. So the focal length now is less than before. So the power will be less, actually greater. So 44.16 centimeters. This is the focal length in a more realistic case, right? And if I was to do the power of the lens, would be 2.26 diopters. All right? It's a typical problem for eyesight, where they give you that. Normally you do this for nearsighted, because for farsighted, the person can look at objects that are very far. So there is not really, when objects are very far, then P is very large. So when for a far-sighted people, by the way, just for you know, normally Q is approximately, where you want the image to be, that's approximately the focal length. Because you are far-sighted, right? So you can look at objects that are very far. For nearsighted, sorry, for this case, right, if you have a far point, this if you have a far point, right? For far-sighted people, sorry, that's different, right? Because the object is close and you cannot see it, so you want to put it farther. All right. Let's do one more. All right. Let's see which one we do now. Actually, let's do this one. Let's do the angular magnification that we talked yesterday. So that one is another problem that is a little bit complicated. And then I will go over some of the problems from homework 14 and 13 and 12 that some people are having some issues apparently. Be careful with the units. Oh, by the way, so let me show you something that is pretty interesting as well. The lenses equation is, as you know, right? 1 over P plus 1 over Q equals to 1 over F. Or in some, for example, in the lab, we had this all right. In any case, remember that the focal length is the radius of curvature divided by 2. If you have that, then this equation becomes, and is in some books, by the way. All right. There is a question, one of the homeworks where they give you the radius of curvature. You have to halve it, or you can use that. Also remember that in many cases, the answer has to be given in centimeters. So even if the information is given in meters, you may have to change it to centimeters, okay? Also, don't forget about the signs. If you're getting it wrong, I don't know how much hints you're getting, but it might be just a sign issue. Also, when you use the lenses equation. So we're gonna get to that, don't worry. But there is a couple of problems I wanna solve that are complicated, so you can see how they're done. This one is not that bad, but uses the idea of magnification and angular magnification. So it's sort of a review of lenses. So what they give you is they give you a leaf. You have a leaf here. It's actually all this. And then you have your axis there. You have a lens. It's almost the size of a leaf anyway. And then your eye. So you are looking at the leaf. The distance between the leaf and the lens, obviously, is 76.9 centimeters. And you are looking at this leaf through the lens at a distance of 1.26 meters. Be careful, look how they're combining the units, right? Meters, centimeters. The focal length of the lens is 41 centimeters. So this lens has a focal length of 41 centimeters. And there are two questions. What's the magnitude of the magnification, the lateral magnification, and what is the angular magnification of by looking at the leaf from here, right? So yeah, so they don't give you the height of the leaf. They just tell you that it's h. So just like that. And by the way, half and half. So we can even say that this is h half. We just call it 2h to make it simple. So this is h and h. All right. Why that's important? Because if that's the case, then we can use our convex length equation, right? That thin length equation. And we know the focal length is 41, it's approximately half of this, there. So we can do this and this. So the image will be here, right? 1 over 76.9 plus 1 over this, right, equals to 1 over 41. So Q is 41 times 76.9 over 9 goes down, 5, 35.9. So we get that in centimeters of. So far we're just working with a length, right? So 41 times 76.9 divided by 35.9, that's 87.8. So Q is 87.8 centimeters. The next step should be changing this to centimeters, right? So if we change that to centimeters, we get 126 centimeters. Why do I need to do that? You will see that in a bit. We can answer part A though. The lateral magnification is your M. So there were questions about that M. I got M is just minus Q, right? So minus 87.8 over 76.9. So you are looking at a magnified leaf, right? Over 76.9 minus 1.14. So that's the first answer. The lateral magnification is minus 1.14. No units, it's just how much bigger. Why minus? Because it's inverted and real. Perfect. So now the question is about the lateral magnification. The image is going to be, sorry, angular magnification. So the angular magnification, well, I need a ruler for this. So is, let's put this guy a little bit farther. There. So remember, right? We found this. This just tells you laterally how the image will be apparently bigger. But every object in real life has 3 dimensions, right? So you're gonna see also that your eye is gonna move. It's gonna cover more area, right? That's what we call angular magnification. That's because if you were looking at this in 3D, or even if you're looking in 2D, right? You have an angle here, let's call it theta 2, which depends on the height of the image, this, and this distance. That's why you need this. 126 minus that, give you that. So 126 minus 87.8 is 38.2. And let's put here height of the image. But that's the image one. How about the object? As I said, we can take the advantage that this part is the same as this part. So let's just use this to show you the angle. The angle for the image was that. For the object will be less, will be what I'm showing you right now here. There. So this is my triangle here. This is the height of the object h, and this is the angle θ1. So the angular magnification, which we label it as, let's just put here, angular magnification, is θ2 over θ1. Right? But if you remember, and given these numbers and the size, you can use that approximation. You can approximate theta to be approximately tangent of theta. That's true. So θ2 will be hi over 38.2. So we have that, right? So this will be hi over 38.2 divided by θ1 on this big triangle will be h of the object divided by the whole distance, which is 126 plus 76.9. So now you're adding all that, right? So the total distance will be 126 plus 76.9, that's 202.9. And then it becomes something like, if you remember here, right? This times that, so hi over ho times 202.9 divided by 38.2. But hi and ho, how do I get this? The height of the image over the height of the object. Here. Right? If you remember, magnification is also what? Hi over ho. So this is that fraction there. Right? So the answer for the problem will be minus 1.14 times 202.9 over 38.2. And let's see what I get. So 202.9 over 38.2 divided by, multiply, sorry. 202.9 divided by 38.2 times 1.14 minus 6.06 approximately. But by the way, for the angular magnification, normally we take the absolute value. You can put in that anyway, so minus 6.06. If they ask you for the magnitude, you take the absolute value. So that's the angular magnification of the leaf. All right. So this part should be very easy to understand, right? The new one was this, the angular magnification. That's why you have to use the figure, right? The angle respect to the image and the angle respect to the object. All right. So I will open this set of problems on WebAssign. Again, they are not going to be graded as part of your homework grade, but you can always use them as practice. All right. For these last applications that we did.
And this won't be on the test, Mark, but it will be on the
This
final.
won't be on the test. This won't be on the test. even for the final, I don't think I would put a problem like that, like this. In the final, there will be problems. There will be one problem about nearsighted people for sure. I'm finding the power of a lens and stuff like that. But this we have never asked, all right? I wouldn't say it's a challenge problem, but I would say that it's a problem that requires a combination of a few things that we have discussed in class, right? And you probably have noticed that, or you will notice that the problems on the final will be even easier than the ones in the assignment, and for sure easier than the ones on the test, all right? Also because of the limited window that you have for the final, right? But again, that's one of the goals of this topic, is to understand all these concepts behind lenses. And now, the other problem that I want to do, that I think is also a challenge, and it's in one of the homeworks that you have in there, is what happens when you combine a lens and a mirror. That one is a hard problem because if you are not explaining what's going on, well, you can have a situation like what happened when I was taking this course in undergrad, when most of us didn't make it through the, it was a midterm, because that required to know what happens when you combine, so that would be assignment 14. A convex lens and a convex mirror is the last problem on assignment 14, all right? When you have a lens and a mirror, right, and this is something that they didn't explain us back then, that combination is used to investigate virtual images due to convex mirrors. If you remember when we did convex mirrors, we always got virtual images. And in a lab, they are very hard to observe. So the only way you can actually get away with it is by using a combination, like we did with a divergent lens, and you did it yesterday in the lab. If you have an object, and then you have a converging, a convex mirror, a convex lens, and a diverging, a concave lens, then the combination of those two, by having a virtual object, allows you to find the image of that, and then you can see a real image, something that is not common for this type of lenses, right? For the divergent lens, okay? So a combination of lenses can be used to overcome that. So let's see what happens with a convex mirror, because we didn't discuss that, right? We didn't discuss how we can use optics and combination of mirrors and lenses. So again, will you see a problem like this in an exam? No. All right, because it will be hard, but it's on the assignment though. So what I'm gonna do is I'm gonna use the numbers I have there, but they are different to the ones that you have. So if you are trying to do this problem, you may wanna follow it by looking at the board. Am I recording this? Yeah. So, and also because of the units they give you. So in real life, you're gonna get situations like the one we just did, or this one, where they give you meters and centimeters combined with each other, all right? Because in real life, you put objects that are not 10 centimeters or 20 centimeters away, but they can be 1 or 1.5 meters away, right? Very distant objects. And this is a good case there. Let's see, that should be here. Okay. So they give you an object, obviously, and you're gonna have a lens, convex lens. You can see how important this type of lenses are as you go through the course, right? Let's say the object is here, 1 meter away, and then 1 meter, you have, what's this? That's a convex mirror. All right. All right. So this is 1 meter. 1 meter. The focal lengths are 79.6 and minus 49.8. So this is plus 79.6 centimeters. And this one has a focal length of minus 49.8. Okay. You can ask this question in several parts. And that's how we got asked this question back then. They asked us first, find the image of this object used to this lens. So you have the focal point, the focal length, sorry. You have the object distance, but this 1 meter. Right? Important. So let's do the math first. So 1 over 100 plus 1 over 79.6, sorry, 1 over Q1 equals to 1 over 79.6. So Q1 will be 79.6 times 100 over 20.4. That's my answer, right? And look what we get if we do our calculations. So I will get over 390.2. So this is 100. But this is 390.2 centimeters. So what is that telling you? I mean, it makes sense. The focal lengths are large, are 100 centimeters. That the object is way over there. Is almost 4 meters. So 1, 2, 3. It's almost around. So it's not going to be to scale, unfortunately, now. It's 1 meter, 2 meters, 3. It's around here. Right? So we can say that the object is, because that's 79, all the way over there, all the way around here. I don't know if you're seeing it there. Let's see. Yeah, you can see. So the image, because of that, of this object is very far. What type of object is that though? Once you put this mirror here, in between the lens and the object, what type of object is that for this mirror? Because this is a real image. But now, this will be the object for this. So, what can you say about the object distance for this mirror? And that's what took us, at least I had some hard time understanding at that point. I knew that it had to be negative. But the question is asking at the end, what's the final image? And the final image on this particular experiment is not due to the mirror. Because the mirror has a focal length, so this is 1 meter, and this will be a hash around here, right? You are now behind the convex mirror, right? It's still a convex mirror, but the way light behaves is not as you may think. It's gonna be so like that, and the focal length is there. It's not there. So it's gonna go like this. So it's gonna be sort of like your concave mirror. And it's gonna go here. So that is the image of this object due to the mirror. But that's an image behind the mirror. You know what happens? So you know what's the extra step? Because there is a lens in front of the mirror, this image is going to project through the lens. And you're going to find an image, a real image here. So your final image will be around here. And I didn't believe it at the end. So when I went to the lab and I put this together, I put the screen here and I found the image of this object upright, inverted around here. Tricky, right? Because that's what you wouldn't expect that to happen. But that's because of how this, so this probably should be more like this. Yes. Like this and then like that. So the object here, right? So this P, which is negative, this was 390.2. So let's put it here. All this is 390.2 minus 100. This P is 290.2 centimeters. But it's actually negative because that becomes now, that is a virtual object. All right. The focal length is negative though. So it makes sense, but we're gonna get this. We're gonna get minus 1 over 290.2 plus 1 over Q2 equals to minus 1 over 49.8. Right? So Q2 will be this times that divided by this minus that, so negative. Negative 290.2 minus 49.8 240.4, and it's negative. Makes sense because it's a virtual image. So again, technically you wouldn't be solving the problem, right? Because you are still getting a virtual image. You want to get a real image. So by combining it now, by remembering that we have a lens in there, so minus 60.1. So this is minus 60, or just put 60.11 centimeters. The minus means that it's still behind the mirror. You know something? If you think about it, right? This will be the virtual object behaving this like a concave. So this is the virtual image of that virtual object. Right? It's still behind the mirror. This is in front of the mirror. This is the real side. So that's where I got stuck. And the professor was so mean that we got all 0 points because we got stuck in that. Right? So I remember getting to this point. What we miss, because this is not the final image. You will think that's the final image, but it cannot be the final image because that's still within the mirror. You have to remember that this image can be projected on this lens. All right, that's something that happens with mirrors and lenses. So we will get this new object distance, which is positive now, because that's the image for this lens now, not for the mirror. So that will be 100 plus that 160.11, right? And then we have the focal length. This combination of these two will give you where is the position of the final image. And Q will be positive, meaning that the object here and the image will be at this point here, right? So your final image, if we do it here, so the final image will be located where? 1 over this plus 1 over Q3 now, the final one, is equal to 1 over 79.6. This should be approximately also 79.7 centimeters. So you're talking about approximately here, right? Wait. Now, approximately 160 centimeters. So we'll be away from here, all the way out here. You cannot see it now, but it's behind the object. And it's inverted. This is positive. This is positive, of course. So it's inverted. And almost, pretty much, the same size as the object. So this will be the hardest type of problem you can see because you are combining now two different objects. You are not combining two lenses. You're combining a lens and a mirror. Can you do this with concave mirrors? No. I tried to repeat the experiment, and the thing is that concave mirrors give you real images. So you wouldn't be able to see the same, right? The reason this works is because convex mirrors give you virtual images. So you are overriding it by applying or by placing the convex lens in there. So at the end of the day, the key element was the lens. The mirror is important to know where is the object that the lens is going to use to project at the end. All right? So this is the last problem on assignment 14, pretty much. All right? I believe what they ask you is, where is the image located? And where is it located, like behind, at the left or at the right of the lens? And then the nature of the image. Right? The only thing that you have to be careful with this, again, is how light behaves inside the convex lens. It is the only case where you are seeing it like that, right? For a convex mirror, the focal point is always inside the mirror. So it doesn't matter where the object is, it's always gonna be projected towards that. So this ray image looks like the concave one, right? That's the other thing that will throw you off, all right? But the focal length is negative. Yeah. And that's another example of virtual objects as well, right? A virtual object is an object that is not supposed to be there, but you can still use it to solve a situation like this. All right? All right. So let's do a revision for some type of problems you might get tomorrow. All right? There were some questions about this one as well, so I want to stay with assignment 14, lenses and mirrors. All right? Let's start with the first question. All right? Remember, to characterize an image, in many occasions, the magnification will be probably the best thing you can use, okay? So let's take a look at that. So they give you a converging lens, so a convex lens, with focal length of 44, and they want you to locate the image and find a magnification. The first one, they give you the object distance of 44. All right. So just by writing the values, right? If the focal length is 44 centimeters and the object distance is also 44 centimeters, then Q is equal to 0. Right? By using so no image. All right. Now if they give you the object distance to 12.6, so the focal length is still 44, but now the object is 12.6. Clearly, look at this case. What you want to see? The Q will be negative. The image distance will be negative. When you solve this, you will get minus over 44 minus 12.6, 31.4. Right? That should give you approximately minus 17.5. So the image is virtual and upright. How do I know it's upright? So I look at the M. What's your magnification? Minus 17.5 over 12.6. So that will be a positive magnification of 1.4. Make sense? If the magnification is positive, the image is upright. It can be virtual and larger than the object. So that's the case that we also will discuss, right? Okay, let's take a look at a divergent lens. So they give you, and we do the ray tracing as well in this one, okay? An object that is, say, 20 centimeters at the left of a divergent lens with focal length minus 30. So remember, for a divergent lens, we don't care about the position of the object. It doesn't matter. The focal length is big. The object is minus 32. So in fact, the focal length is actually way here. About here. All right. The object is here. It's located 20 centimeters away. And the focal of this guy is minus 30. The only thing you need to remember is this. Whatever goes here gets diverged. Like that. But we always extend it towards the focal point there. And then we have this.
So the focal point being negative doesn't mean it's to the right of the lens, or doesn't mean it's to the right of the lens, and then we transfer it over to the left of the lens to draw?
For all lenses, there are two focal points. The difference is because there are two surfaces. For the mirror case that we just had, right? There is only one surface, the one here. So the focal point is just the one there. Think about in terms of a parabola, all right? A mirror, a parabolic mirror, like the antennas that you guys have, right? For a cable or TV or satellite, they are paraboloids. A paraboloid is a 3D parabola, but they have the same shape, it's a parabola, right? The focus, which is the point where the antenna is getting all the signal, right? It's always inside the parabola, it's only one. For the lens, imagine two parabolas come together. So you have two focal points. The one for this surface and the one for that surface. So there are two surfaces here, right? So you have focal point there and then also here. But for a diverging lens, you don't use this one here, never. You use this one here. Because the rays are diverging. This one goes straight, but this one hits and diverges. But it extends through the focal point now.
So is the negative sign that's given, is that really just to help us with the algebra, but we need to remember to make
It's
the
for
focal
the
point?
algebra. Yeah,
Okay.
it's for the algebra. And also, to realize this, what I'm drawing right now, that the image is what? Virtual. With some exceptions, the object distance is always positive. I don't always like to say in lenses that the object is always positive, because we have seen already at least two cases where we have virtual objects. But that's a special cases where you have combinations and such. If you have only one lens, P will always be positive. In order to have a virtual image, the focal length has to be negative. All right? If you do the algebra, you will see 1 over 20 plus 1 over Q is minus 1 over 30. This will go there as negative, so then you will have a negative regardless. So it's an algebra, it's helpful for the algebra, yes, but it's also a conceptual. It has its meaning behind the concepts of how the images are formed. So the image will be 30 minus 30 times 20 divided by 50. So 18, right? 12 minus 12 centimeters. So this is 12. Can you observe that image? You can, right? You cannot observe the image because it's virtual. For people who did a lab yesterday, or they're doing it today maybe, normally there is an experiment where we do diverging lenses. But the only way you can actually get out of it information is if you're actually doing it. That's why this semester we decided to remove that. That's why the lab seemed a little bit short, right? But there are divergent lenses sections in the lab. There's one at least. Are lenses clear now? And mirrors? Because there's a combination I want to do here again.
Can you show me how you got the dashed ray? You went through the focal length, the focal point.
Dash ray is basically, you get it by knowing that light, right, is parallel to the axis, then hits the lens, and then diverges. So as you diverge, as light diverges, you extend. And this is extend towards the focal point, always. So the way light diverges on the lens, in the lens, sorry, is by following the focal length, the focal point. It's not randomly. It wouldn't go like this or like that. It will follow the location of the focal point. So you expect,
Okay, thank you.
all right? All right. Okay, so let's take a look at this again. Okay, this is a good one. So this word problem. So they give you two converging lenses. Each one has a focal length of 15 centimeters. So you are given two converging lenses with focal length both 15 centimeters. And they are placed 40 centimeters apart. And then the object is in front of one of the lenses 30 centimeters away. So they are 40 centimeters apart. So if you were to graph this, one there, one there, this is plus 15, plus 15, and these are 40. The object is placed 30 centimeters away from the, so this is 40, 30, 40, 30, about here. This is the type of problem you can get in exam, by the way. It's an easy problem. We did one like this yesterday. And on top of that, I might even ask to draw the whole ray image there. So we're gonna find the location of the image, the magnification, and we're gonna characterize the image, okay? Half the focal length, right? Remember, there are two focal points. So the focal point is here, here. So I will first do this. It doesn't have to be to scale, by the way. All right. That's there. I might have to move the other lens so it looks better. You start like that, and then you use the lenses equation for this. 1/30 plus 1/q equals to 1/15. So q is 30 q1. So this is 30. How much is this then? That's 40. 30. This is 10. in previous semesters, what I noticed is that everybody does this part correctly, but they forget to analyze this. And what they do is that for this lens, they use this as the object distance. And it messes up the whole problem. Because the object distance now, for this object and this lens now, is going to be 10. But remember that the focal length was 15. So the object is within the focal. So let's call this F1, F1, F2, there. And then in fact, we can say that there is F2 here, right? So if you remember, I did something like this yesterday. I said this goes like that, but you also have this, right? Do they intersect over there? No. One is going like this, the other like that. So what do we have to do? We have to come back. Like this. My image is going to be approximately here. It might not be there because I kind of twisted it a little bit. So let's see. How do we know? So the second part will be my P2 will be now 10, and my focal 2 is 15, right? The same. So 1 over 10 plus 1 over Q2 equals to 1 over 15. So the second object distance is minus 15 times 10 over 15 minus 10, 5. Minus 30. So close should be probably more like here. The image will be around here. 30 centimeters away. All right. So virtual. If you were going to look at the object from this side, you will look at that image at the end. All right. That's basically the compound microscope there. So there it is. The image is inverted and virtual, the final image, right? And then you want to know if it's going to be what magnification has. The magnification is here. Total magnification will be M1 times M2. M1 will be minus Q1 over P1, so the first image and object distance, and then minus Q2 over P2. Right? Oh, but that's minus that, right? So let's put it here. So minus 30 over 10. Minus and minus positive. It is minus, negative. This is 1, negative 3. So the image is 3 times bigger than the object. Any questions about that? We did the 2 situations, right? We also did it if you have a real image at the end. And it's here. But this one is also very interesting. All right, so 2 converging lenses, they can behave like that. Are there any requests or anything you want me to review? Maybe refraction or maybe mirror questions?
Professor, I have a quick question about a previous example, the one where the image is virtual and upright. That it was like 2 problems ago. For that one, was that a mirror or a conversion lens?
That was a convergent lens.
Okay, thank you.
Yeah. But you can also have upright virtual image due to a concave mirror. Remember the dentist problem. It's not in the assignment this semester, but in the book, I'm pretty sure you can find that. Let's see if I can do it here. So that's a mirror type of question now. The dentist or the barber problem, right? The one that they use to magnify your tooth, or the one that you use to magnify your chin. You place yourself close to the concave mirror to magnify, and then it's easy for you to shave, right? So it's actually a review of concave mirrors. Like that. So that's the comment. So basically, you have the focal point and the center of curvature there. And then they ask you to find the focal length of this mirror. So if you place a tooth, right, or an object, say, how close can it be? 5 centimeters. The image is magnified three times. Find the focal length so that happens. So let's remember our ray tracing for concave mirrors. We sort of did it with that problem that we did before, right? But remember, and then goes through the focal point. So let's use this to big there. Like that. Right? And then you cannot use the F-ray. So what you do, and this actually gets projected, gets extended. When you use the C-ray, the one that goes through the center. What's the property of the C-ray? Is that the rays, they get bounce, reflected, and bounce on the same. There is no other rays going on there. So you have an image here. That image is virtual because it's behind the mirror. Don't get confused with lenses, all right? So that's the difference. So now the image is virtual. And up, so this is upright, obviously, and virtual. But we also want it to be 3 times as big. So 3 is a magnification, which is minus Q over P. But P is fast. So how much is Q? So then to find the focal length, $7.5, right? $15, 2, yeah, 7.5 centimeters. There you are. That's a situation with concave mirrors. All right. Any questions about that? Let's actually check some of those refractions. So we've done all 14 and 13 here. 13 was mirrors, so was that. 12 is reflection and refraction. And I remember doing all the prisms here, and the critical angle and the apparent depth. But let's review the prism question. All right. I hope that you guys are also making already an equation sheet. All right. The best way you can do it is like the booklet we would provide you guys if you were on campus, where you have the list per topic. All right. And eventually you should join it with a physics 1, right? So you have your vectors, your kinematics, your Newton's laws, gravitation, temperature, all that. But then for this part of for this course, you have electrostatics, you have, electric fields, Coulomb's law, energy, potential electric, your capacitors, your equations for capacitors, and then you go to current, resistors, power, and then you go to circuits, RC circuits, and then you have all the magnetism equations, right? Including, which is going to be tomorrow, by the way, the RLC and AC circuits, LR circuits, inductance, a little bit maybe on generators, and then you can go into the optics part. Electromagnetic waves is only C equals to lambda F. It's not going to be there tomorrow, but there might be a question on that at the final, right? And then optics is just what? 3 equations that you need to know. It's more about the situation. So one of the main differences between optics and the previous topics is that in the previous sections, it was mostly about finding the right equation, right? But in here, even though many of the problems, you don't really need to draw them, I always tell students it's a good idea if they do, all right? Because it helps. It helps a lot, especially when you have combinations. So a 45-45 prism with an index of refraction of 155. We're going to have light going and then being refracted and then being refracted back, right? So light goes like this, it gets refracted. Now, this is the thing though, when you want to refract, you may want to have your normal, but this is the thing though. The normal for a 45-45 prism, and let's see if you remember this from geometry, has to go through the vertex. So, your normal has to be this. Why is that? Can anybody guess why it has to go through the vertex? And then obviously light goes like this, gets refracted, and then the normal here and then gets refracted away. So they want this X here. All right.
So you form another triangle?
Yeah, it's because
Fine.
45, 90, right? What's the angle here? 45. 45, 45. So this normal happens to be the median, bisector, and I don't know how you call the other line. But there are all those lines, right? Because it's a isosceles triangle. It's a right triangle. It's an isosceles right triangle, 45, 45. In any case, that also helps you to find the angle of incidence. What's the angle of incidence? If this is parallel to the base. Tomorrow you may have to think about that, by the way.
45.
45, right? So 45, that's 45, but only this is 90, so that's 45. All right. Before we solve for this angle here, theta, it's called theta 1. The two normals intersect here. 90, 90, 45, you're gonna need this angle here. Let's find theta 1 while you think about that. 1 times sine of 45 equals to 1.55 times sine of theta 1. Remember, tomorrow your calculators have to be in degrees. Also, there was a question about the generator one that a lot of people got, and I actually gave you partial credit for that. I want to take a look again at the numbers, but I believe it was 50 milliseconds, right? When you have, well, I will go back to that problem so I can explain you what I mean. So 0.45 and then 27.14 degrees. So that angle is 27.14. The obtuse angle there, in this quadrilateral here, right? This one here. Right? All that is 360, right? 90 and 90, 180. Plus 45, 225. 360 minus 225 is 135. Right? Let's double check just in case. Yeah. So now we have 135 plus 27.14, 162.14, 180 minus that, 17.86. So the angle of incidence now here, let's call it theta 2, is 17.86. How do I find x? If there is an x, because let's see what happens, right? By Snell's law, 1.55 sine of 17.86 equals to 1 sine of x. Let's see. It might be the critical angle. We don't know. Okay, no, it was fine. Wait, why so low? Okay. So I get 28.4 degrees. Yeah, I guess it makes sense because that was present. All right. Remember, there can be a case where maybe it's not very common in right prisms. But remember, in the equilateral prism, we can have a situation where when you have something like this, you can have a situation where it goes like this, or it goes total internal reflected, right? That's when you approach the critical angle. Okay. All right, so let me take a look at that problem. It's in assignments. I just want to take a look at the frequency. It was 100 pi. So they give you a 50 hertz generate frequency. So 2 pi f will be 100 pi, and then 5 milliseconds. All right. So sine, all is everything you notice is in degrees, but when we did generators, and maybe the problem is that we didn't do one situation where we replace an angle of here, when these 5 milliseconds, you get here, don't you get that? 1,000. Yeah. What's the sign of that? I think what some of you did is you multiply the whole thing by pi, and then you got the sign of this, right? Like if it was degrees, and you got the other answer. I think it's like 2 point something, or 27.4, 2.74. That was so.
This was on the test, Professor?
Yeah, that's on the test, on the second test. The answer was 88.9 volts, the maximum. Whatever you have here. So that was the idea. That's why I put a number in particular, 5 milliseconds. If you do a multiplication, you get sine of pi over 2. Pi over 2 is 90 degrees. Sine of 90 is 1. All right. So if you were to see something like that again, that's how you solve it. All right. Then I don't think there was any other thing here. Yeah. And we went over the directions. All right, guys. So I think that should be good for tomorrow. All right. Optics and RLC circuits. So far 5 questions. I might put a 6th question there. All right. But they are all very similar to what we've done in class. All right. Bear in mind that in some cases I might ask to okay, yeah, so then that will be the problem. So you need to include negative signs in your answers in Cengage. Yes, you need to. All right. They even tell you, I think, in some cases, to remember the characteristic of the image. So that will make a change. In any case, in some cases I might ask you to draw the array images. In some cases you may not. But remember that the algebra, the magnification gives you a lot of information about the image. I'm doing office hours today, by the way. Should have told you that at the beginning. I'm doing office hours mostly for the lab, but I'm going to invite everyone, also from lecture, around 3 or 3:15 p.m. today. All right? It's going to be approximately for 45 minutes to an hour. So if you have any questions, you can bring them there. All right? But you have all the information needed now for the exam. The only thing I'm going to do now, after the exam on Monday, so tomorrow is the exam on Monday, we're going to do a little bit of wave optics. So we're going to introduce interference and diffraction. And then that's it. We will do a review on Tuesday, and then on Wednesday you have your study day. And again on Wednesday, I will be available for questions. All right? You have the weekend, and if you need any help during the weekend, please let me know by Friday. All right? So I can separate some time to maybe meet with you, anybody, for a few minutes on the weekend. All right?
Can we email you questions over the weekend?
Yes, you can. Yes, that's fine. But again, for the weekend, and I think that's for every professor, you need to allow 48 hours for the answer. Maybe 24 for this weekend, because I know it's the final. All right? But yes, if I see them right away, I will try to answer them right away. Okay? Are there any questions about tomorrow or what we've been doing?
I I have a quick question about the one that you just went over from the test about the sine. I'm not getting 88. I keep getting the 2.43.
Okay.
Sure.
The maximum?
Yeah, for 6B, which is to calculate it at 5 milliseconds.
What do you got for 6A?
I got for the expression E equals 88.8 sine, and then omega,
Okay.
which is 314.2.
This is the thing though, that's what I'm saying. What you are getting right now is this, right? So 88 point what?
88.8.
Sine of that. 100 pi t, right? That's the right answer for the first part. It's part A. Part B is asking you to evaluate when t is 5 milliseconds. So that's what I did there. 88.8 sine of, so this is why I said that I should have told you before. You don't put pi as 3.14, just leave it as pi. 5 milliseconds. If you multiply this, you get sine of pi over 2, which is 1. What's 1 times 88.8? 88.8. So you have to leave it in radians. That's the thing. And it's not you. I think almost half the class got that mistake. But I didn't take too many points off them.
Thank you.
All right? So that's how you evaluate expression, guys, in generators, right? You have to leave it in radians. Yeah. All right, guys. So let's stop the recording.